Okay, so hello students. The chapter that we are going to take up today is the triangles. And in triangles in class 9, you have studied about congruency of triangles. So we'll extend that. And in this class, we are going to take up similarity of polygons and similarity of triangles. And before getting into the similarity of triangles, we'll be first taking up the Thales theorem or the basic proportionality theorem as it is called, and some of the corollaries that are related to it. After that, we will take the similarity of triangles, wherein we'll be looking at the criteria for similarity, which include the angles criterion, the side criterion, the side criterion, and some related theorems. Besides that, we will be also taking up some theorems and some concepts related to the areas of triangles and their ratios. And lastly, for this chapter, we'll be taking up Pythagoras theorem, and we'll be looking at a few concepts that help us understand the theorem better, and also a few practical applications of this Pythagoras theorem. So this is what the whole chapter on triangles is going to cover, and it will be divided into a few concept lectures. So let's begin with the first concept lecture with the similarity of polygons. Now, what are polygons? Polygon is any closed figure with defined sides. So two polygons are said to be similar if they have same number of sides. So any two polygons can have any number of sides. So you have how many sides? You have a pentagon here. This pentagon and this pentagon would be called similar. They are not congruent. Congruent is when they both superimpose. When you superimpose the two given figures on each other, they'll exactly match. That is called congruency. Here, if you try to superimpose, it's not going to exactly match. Hence, it is not a congruent. These two figures are not congruent, but they look similar. And how do you define what similarity is? Similarity is when the two polygons have the same number of sides. So the first thing that we need to look at is if they have the same number of sides. So both of them have 5 sides. So we can say that this criteria is met. The second criteria is that their corresponding angles are equal. So if this is a regular polygon, or if I say that this is 90, this is 90, these two angles are 90, let this be whatever, these two angles may be same. I'm not giving you the exact values because I'll have to match it. I'm just keeping it as x and y here, okay, just for understanding. So if these angles are also same, so the corresponding angles are equal, which is true in this case, and also if the corresponding sides are proportional, that is, they are in the same ratio. So if this side by this side is equal to this side by this side is equal to this side by this side is equal to this by this is equal to this by this, then these two figures will be called similar figures. So they'll be called similar pentagons if these three conditions are met. If all these three conditions are met, then the two pentagons are going to be called similar. So they'll be called similar pentagons. And if you name them, for example, if this is named as A, B, C, D, E, and this is named as, say, P, Q, R, S, T, then we can say that polygon A, B, C, D, E is similar to polygon P, Q, R, S, T. Now this symbol is used for similarity. If you remember in class 9, we used this symbol for congruency. So there was this sinusoidal wave kind of a thing and an equality sign below it, which meant the two figures are going to be congruent. If you remove that equality, that means they are similar. So if this is there, it means that the two figures on the two sides of this symbol are going to be similar. Now, in case of triangles, when I say triangle, it is a polygon with 3 sides. So the first condition need not be stated explicitly in this similarity of triangles. So here what we see is there are just two criteria that need to be fulfilled. The first is that the corresponding angles of the triangle are equal, And the second is that their corresponding sides are proportional, that is, they are in the same ratio. They need not, we don't need to explicitly state that they should have the same number of sides, because a triangle by default will have 3 sides only. So that condition does not need to be stated separately. That is implied in it. Now, when we go ahead, when we will look at the similarity of the triangles, we will see that if one of these conditions is true, the other one automatically becomes true. So if in two triangles, the corresponding angles are equal, then their corresponding sides will automatically become proportional. And if the corresponding sides of two triangles are proportional, then their angles, corresponding angles, will also become equal. This is what we will be taking up in one of the proofs when we do. So we'll save it for later. But remember that in case of triangles, if you prove one of the two conditions, the other is going to be implied within it. So you just need to prove one of the conditions, the other is going to be true by itself, either of the two. Okay, so you don't need to prove both of them separately. Now that you know that similar figures are, or similar polygons are, can you tell me in these two figures if they are similar or not? What do? We first check out if they have the same number of sides. So they both have 3 sides. So the first criteria is met. The second one was that their corresponding angles are equal. Now this 90, this is also 90. So these two angles are equal. Now what about this angle and this angle? If you remember from trigonometry, if I call this alpha and if I call this angle beta, what is tan alpha going to be? Tan alpha or sine alpha going to be? It's going to be, tan alpha is going to be 8 by 6, which is 4 by 3. And similarly, tan beta is going to be perpendicular by base, so it's going to be 4 by 3. So tan alpha is equal to tan beta, and then you can prove that alpha is equal to beta. So two angles are equal, so the third angle would also be equal, because in a triangle, the sum of the angles of a triangle is 180 degrees. So if two of the angles are equal, then the third would also be equal. So here we see that the figure has same number of sides, or angle bhi dono ka equal. And the third criteria was to check whether their corresponding sides are proportional. So the corresponding sides in these two triangles will be, we have to check if PQ by AB is equal to PR by AC is equal to QR by BC. Is it? PQ by AB is 8 by 4, that is 2. PR by AC is again 10 by 5, which is 2. And QR by BC is 6 by 3, which is 2. So all the three conditions are satisfied. Hence we can say that these two figures are similar to each other. Now coming to the second question. Here we see that this is a parallelogram. Both of them have 4 sides. So the first criteria is met. Their angles do not correspond. The corresponding angles do not become equal. So here all angles are 90. Here they are not. Right? This is a parallelogram. Here the angles are not 90. It's not given as 90. Okay? Although the sides are in the same ratio, but their angles are not equal. The corresponding angles are not equal. The second criteria is not met. Hence, these two figures cannot be called similar. So all the three criteria need to be matched. They all have to satisfy. They have to be satisfied. Now, in this particular question, in the third one, again, the sides are 4. The angles we see are equal. The corresponding angles are equal. And what about the sides? 2.4 by 4.8 is 1 by 2. 2.1 by 4.2 is 1 by 2. 1.5 by 3 is 1 by 2. And 2.5 by 5 is 1 by 2. Hence the corresponding sides are proportional, the corresponding angles are equal, and the number of sides are equal. So again, in this particular case, the two figures are similar. So this is how you figure out whether two given figures are similar or not. I hope you got it. Okay. So now we are going to take up the Thales theorem. I hope what similarity is clear to you. Once again, to recap, two polygons are said to be similar if 3 conditions are met. The first is they both should have the same number of sides. The second is their corresponding angle should be equal. And the third is the ratio of corresponding sides is equal. That is, the corresponding sides are proportional. If all these three conditions are satisfied, that means the two figures are going to be similar. In case of triangles, we need not specify explicitly that the two figures should have the same number of sides, because the triangles would anyways have three sides. Okay, so there are just two criteria. One is the corresponding angle should be equal and the corresponding side should be proportional. I also said that in case of triangle, the truthfulness of one would imply the truthfulness of the second criteria. So if the corresponding angles of two triangles are equal, then automatically the corresponding sides will be proportional. And if the corresponding sides are proportional, then by default the corresponding angles would be equal. You need not prove both of them separately. Alright, now let's move to Thales theorem. Okay, now coming to the Thales theorem. What does the theorem say? It states that if a line is drawn parallel to one side of a triangle, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. So what it says is, given a triangle ABC, suppose there is a triangle ABC, if a line DE is drawn parallel to BC, then AD, the two sides AD, AB and AC will be divided in the same ratio. So what it says is, we have been given triangle ABC and DE is parallel to BC. This is given, and we have to show or to prove that AD by BD is equal to AE by EC. This is what you mean when you say that the other two sides. So if BC is parallel to D, what are going to be the other two sides? The other two sides are AB and AC. And it said that if the AD is parallel to BC, then the other two sides, which is AB and AC, are divided in the same ratio. And how are they divided? They are divided by the points D and E. So it says that you have to prove AD by BD is equal to AE by EC. And if you prove this, this is what the Thales theorem is. This is what Thales theorem is. And it's also called the basic proportionality theorem, which we will be writing as BPT. For once, I'll write it here. It's called basic proportionality theorem. Okay. So this is what it is, and in short, we call it BPT. How do we prove it? For proving, we need to do a construction. In the figure, it's already done, but the construction is EN perpendicular to AD and DM perpendicular to AE. Okay, so these two constructions we do. What we do? We drop a perpendicular from the point E on the side AB. So it meets AB at point N, and the other perpendicular we drop from D to the side AC. So it is DM, which is perpendicular to AC or AE, since A is a part of AC. Okay. So now this is what the construction is, and then you join the dots, join through dots C and D and B and D. So that's not a construction, it's just a joining of these points. Now, what is the proof? How do we prove it now? Let's start the proof. How do we do it? Now, area of triangle, if you take here, the area of triangle ADE, area of triangle ADE is what? Area of triangle ADE is half into base, which is AE, into height, which is DM. Okay, in triangle ADE you have perpendicular and the base, so you have area of triangle AD equal to AE half into A into DM. Okay, and area, what does area of CDE equal to? Triangle CDE, this is the triangle, its area will be half into the base is CE, the height again is DM. Since this is one of the vertices of the triangle, How do you find the perpendicular? You drop a perpendicular to the extended line, extended side, so you have MD. So area of triangle CDE would be half into base into height. This perpendicular does not fall inside the triangle, it falls outside on the extended part of it. Okay, so you have half into CE into DM. All right, now when you divide these two, what do you get? When you divide these two, you get area of triangle ADE by area of triangle CDE is equal to DM and DM would cancel out, half and half would cancel out, and you will have AE by CE. So this is the first equation that we get from here. Similarly, again, if you go, area of triangle ADE in this triangle is also half into AD into EN, because this is also a perpendicular. This could be the base for it. So you can also say that area of triangle AD is half into EN into AD, right? Just like it is equal to half into base AE into MD, it can also be AD into EN. And what will be the area of triangle BDE? The area of triangle BDE is going to be half into base, which is BD, into EN. BDE, again, from E we drop a perpendicular. So for this side, this is going to be the perpendicular. So it will be half into base, which is BD into EN. Again, here also the perpendicular falls outside the triangle for which we are trying to find out the area. Now take the ratio of these two triangles. Again, you have area of triangle ADE by area of triangle BDE equal to, again, half and half would cancel out, EN would cancel out, and you'll have AD by BD. Now this is number 2. Now, if you look at the triangles BDE and CED, triangle BDE and triangle CDE are on same base and between same parallels, aren't they? The base is same, the base is DE, and they are between the two parallel lines DE and BC, which will imply that area of triangle BDE is equal to area of triangle CDE, because they lie on the same base and between the same two parallels. Now when these two areas are equal, what do we infer from these three equations? If you look at these two, you would see that both of them have triangle ADE in the numerator. You would see that both of them have triangle AD. I'll just change the ink color so that we are able to get it better. Okay. So what we see here is both of them have triangle ADE in their numerator. Also in the denominator you have triangle CDE and triangle BDE. And we found out that both of them are equal. So the left hand side of both equation 1 and 2 are equal from 3, right? From equation 3, we see that the left hand side of both equations 1 and 2 are same, because the numerator is already same. They both have triangle ADE in the numerator. In the denominator, they have triangle BDE and CDE respectively. And we have found in number 3, the equation number 3, that both of them are equal. So from using 1, 2 and 3, what do you say? What do you get? Using 1, 2 and 3, we have, what do you have? AE by CE is equal to AD by BD. And this is what we had to prove. And hence we can write that hence. So this is what we had to prove, and this result, this particular result, that if in a given triangle ABC, if in a given triangle ABCD parallel to BC, then AD by BD is equal to AE by EC. This is always going to be true as we have proved here, and this particular result is called the Thales theorem or the basic proportionality theorem. I hope you got it. Now, after the Thales theorem, we are going to take the converse of this particular theorem. Just to recap once again so that you get it clearly, the Thales theorem, also called the basic proportionality theorem, states that if a line is drawn parallel to one side of a triangle to intersect the other two sides in two distinct points, the other two sides are divided in the same ratio. So you have a triangle ABC given in the figure where DE is parallel to BC, and we have to show that AD by BD is equal to AE by EC because D and E divide the two sides in this ratio. So this is what we have to prove. The first step is constructing two perpendiculars EN and DM perpendicular to the sides. So you have DM perpendicular to AE or AC and EN perpendicular to AD or AB. Now coming to the proof, in the first case we take triangle ADE. So the area of triangle ADE is half into AE into DM. If you take the perpendicular DM into consideration, the area of triangle AD is going to be half into AE into DM. Now triangle CDE's area will be half into base into height, which is half into CE, which is the base, and the perpendicular from D on CE extended, which is DM again. Now take a ratio of these two areas. So you have area of triangle ADE divided by area of triangle CDE is equal to AE by CE. Why do you get AE by CE? Because this half gets cancelled out, the DM gets cancelled out. So you get AE by CE. We call this equation 1. Again, coming back to the triangle ADE, we have its area equal to half into EN into AD. This is another way of finding the area of the triangle ADE because this is the second perpendicular, which is EN. Now, similarly, triangle BDE's area will be half into EN into BD. Now, take the ratio of these two areas and you get area of triangle ADE by area of triangle BDE is equal to AD by BD. Now, we get to the triangles BDE and CDE and we see that both of them lie on the same base and between the same parallels DE and BC, which means that their areas would be equal as two triangles on the same base and between the same parallels are equal in area. This we have studied in class 9. So we'll be making use of that result. So using 1, 2 and 3 together, how? When triangle BDE's area and triangle CDE's area are equal, what we see from equation 1 and 2 is that both of them, their left hand sides has triangle ADE in the numerator. In the denominator you have triangle BDE and triangle CDE. And from 3 we have found out that both these are equal, hence the denominator also becomes the same, hence the left hand sides of both the equations become same. So from 1 and 2 we can say that AE by CE is equal to AD by BD, which is what we had to prove. And this proof is called Thales theorem. Okay. Now let's get to the converse of this theorem. What does converse mean? Converse means that the opposite is given. So it's given that a line divides any two sides of a triangle in the same ratio. So the line DE divides two sides of the triangle AB and AC in the ratio AD by DB, and that is equal to AE by EC. So it's given in this case. So in this particular case, it's given that AD by BD equal to AE by EC. And we have to prove that DE will be parallel to BC. So this thing, when DE was parallel to BC and we had to prove this, it was called Thales theorem. And in here we have the opposite thing. So you have AD by BD is equal to AE by EC, and we have to prove that DE is parallel to BC. And this is called the converse of the Thales theorem. How do we prove that? Again, the construction is similar. So you construct the same thing. You have the construction. The construction here is again perpendiculars EN and DM on sides AB and AC respectively. So we construct the same two perpendiculars and then we join CD and B. This is not construction, this is just simply joining. So it's already there, we just join. Construction is when you completely create something new. So the perpendicular wasn't existing, we created, we added it. So that is called construction. Joining CD and BC is not called construction. Okay, so be clear about that. So now let's get to the proof. Again, you have to take the area of triangle AD. So area of triangle AD, just as in the case we discussed last time, would be half into DM into AE. And area of triangle CDE is going to be half into DM into CE. Isn't it? Just like we did in the last case. Again, we take the ratio. So you have area of triangle ADE divided by area of triangle CDE equal to AE by CE. Okay, so we have this as the first equation. Similar to this, again you have area of triangle ADE is equal to half into, what would it be? EN into AD. And area of the second triangle, what did we take? It was BDE. And in here the area is going to be half into base, which is BD, into EN. Again we take the ratio, so we have area of triangle ADE by area of triangle BDE is equal to AD by BD. Here it's given this ratio is equal, right? So from 1 and 2 we see that the right hand sides of both the equations 1 and 2 are equal. So from, what do you have from 1 to 3? We have area of triangle ADE by area of triangle CDE equal to area of triangle ADE by area of triangle BDE. This would get cancelled out. Therefore, you have area of triangle CDE equal to area of triangle BDE. And they have a common base. Alright. So combining these two, we can say, if these two are combined and called the equation A, so we can say from A that BE is parallel to BC. If there are two triangles on the same common base whose areas are equal, then the lines DE, if you draw a line parallel to DE and joining the two, or if you draw a line joining the vertex of the two triangles, it will be parallel. So from A we have DE parallel to BC, and this is what we have to prove here, and hence it is proved. Thus the converse of the midpoint of the basic proportionality theorem is proven. What did we do? Let's revisit it again. Just like in this last case, we do the similar construction. What is given? It is given here in this case is that AD by BD is equal to AE by EC. So a line DE, it divides the two sides of a triangle in the same ratio. So AD by BD is equal to AE by EC, and we have to prove this, that this line is parallel to the third side. So DE is parallel to BC is what we have to prove. Now, similar to the proof of Thales theorem, we first construct the two perpendiculars EN and DM, okay, on the sides AB and AC, and also we join the points CD and B and E. After that, we take the area of triangle ADE. Area of triangle AD is half into base, which is AE into DM, and taking triangle CD into consideration, we have its area equal to half into base, which is CE, and height, which is the perpendicular dropped from the third vertex to the opposite side, which falls outside the triangle, and it is equal to dm. So you have area of AD equal to half into dm into AE, and area of CD equal to half into dm into CE. When you take the ratios, half into dm is going to cancel out, and you are going to get area of triangle ADE by area of triangle CDE equal to AE by CE. This is what you are going to get. Okay. Now again, area of triangle ADE is also equal to half into base, which is AD into EN. And area of triangle BDE is going to be half into base, which is BD, and the perpendicular drawn from the opposite vertex to the opposite side, which is equal to EN again. So you have area of triangle AD equal to half into EN into AD, and it is also, and area of triangle BDE is going to be half into BD into EN. Take the ratio of the two and you get the equation 2 for us, which is this. You have area of triangle ADE by area of triangle BDE equal to AD by BD. Now you have three equations here. Okay, one is given, so the ratio is same, and you obtained two other separate equations. We see that in equations 1 and 2, the right hand side are equal. So the left hand side would also be equal. Thus we write triangle area of triangle ADE by area of triangle CD equal to area of triangle ADE by area of triangle BD, which is the right hand, which are the two corresponding or the two respective left hand sides of the equation 1 and 2. The numerators are same, so they cancel out straight away, and we get area of triangle CDE is equal to area of triangle BDE. We also see that both these triangles CDE and BDE have a common base. They have a common base. So if they have a common base, if two triangles share a common base and their areas are equal, then DE is going to be parallel to BC. That is, these two triangles are going to lie between two parallel lines, and in this case, the two parallel lines are DE and BC. Hence, we have proved that DE is parallel to BC, which is the converse of Thales' theorem. Alright. Okay, so now based on our knowledge of the Thales theorem and the converse of the Thales theorem, there are a couple of corollaries or results derived from that theorem which we can use directly in our problems. Let's see what these are. The first corollary is actually presented in the form of a question in the NCERT book. So you have, the question is that if a line intersects the sides AB and BC of, instead of D, this is going to be triangle, it's not D. So you have, if a line intersects AB and AC of triangle ABC at D and E respectively and is parallel to BC, then AD by AB is equal to AE by AC. Now from Thales' theorem, we already know from Thales' theorem what we have. We have, since DE is parallel to BC, therefore we have AD by BD is equal to AE by EC. Okay, this we can say straight away from, we have already written. So from Thales' theorem we can use this result directly. Now we can add 1 on both sides of this relation, this equation. So adding 1 on both sides of the equation is not going to alter our equation in any sense. So we add 1 to both sides. So add 1 to both sides. This is what we do here. Once we add, we take the LCM. So what do we get? We get BD plus AD divided by BD is equal to AE plus EC divided by EC. You take the LCM and write. So what is BD plus AD? BD plus AD is nothing but AB. You have AB by BD is equal to, and what is AE plus EC? It is AC. So you have this. Okay. So you have AC by EC is equal to AB by BD. Now you take, this is given to be 1 and this is given to be 2. Now you divide these two equations. So when you take 1 divided by 2, what do you get? On the left hand side you have AD by BD divided by AB by BD, and on the right hand side you will have AE by EC divided by AC by EC, which will make it AB. On the left hand side you'll have AD by BD into BD by AB. Once you divide, you take it up, it will become this. So you have AE by EC into EC by AC. The EC would get cancelled out, the BD is going to get cancelled out, and what do we get? We get AD by AB equal to AE by AC. Okay, and when you take, this is what we have to prove. Okay, so we have to stop here. So this is what we had to prove, hence we write hence proved over here. Okay, so let's see what we did here. We know from the Thales theorem that in case the triangle, in a triangle DE is parallel to BC, we have AD by BD is equal to AE by EC. This we can straight away write from the Thales theorem. Once we do that, we add 1 on both sides of the equation. So adding 1 on both sides of the equation, we get this. We take the LCM and take the sum on the numerator. So you have on the numerator side you have BD plus AD. In the numerator you have BD plus AD, which is nothing but AB, and on the right hand side you have AE plus EC, which is nothing but AC. So you get AB by BD is equal to AC by EC as the second equation. Now if you take the equation 1, which is already given we already know from the Thales theorem, it's not given, we know it from the Thales theorem. So you have 1 and 2, and you divide both these two. So you have on the left hand side you have AD by BD, and in the denominator you'll have AB by BD. And the right hand side you have AE by EC from the equation 1 and AC by EC from the equation 2. So take the division. Now you have AD on the left hand side you have AD by BD divided by AB by BD, which becomes BD by AB. You take the reciprocal, you convert the division into multiplication sign. Same happens on the right hand side. The BD gets cancelled out on the left hand side and the EC gets cancelled out on the right hand side. And you are left with AD by AB is equal to AE by EC, which is what we had to prove. This result you can use directly in the questions that you are asked. Okay, so this is a corollary, it's derived from the theorem, so you can use it directly. And what does it say? It says that in a triangle, if DE is given to be parallel to BC, then AD by AB is equal to AE by AC. Alright, Thales theorem says that AD by BD is equal to AE by EC. So it only talks about the parts, but using Thales theorem we have proved that in case DE is parallel to BC, then AD by AB is equal to AE by C. This is what the case is going to be. Okay, so this is a corollary that you can use in the questions. The second corollary, it says that if the vertical angle of a triangle is bisected internally or externally, the bisector divides the base internally or externally into segments which have the same ratio as the other sides of the triangle. Now, this seems to be a bit complicated, so let's just take it one by one. So you have a triangle ABC. Just concentrate on the figure 1. You have the triangle ABC in which AD bisects the angle A. So you have angle BAD, which is this angle, equal to angle DAC. It's given that the vertical angle of a triangle is bisected by the line AD. And in that case it says that this bisector, which is AD, divides the base, which is BC, in the same ratio as the other sides of a triangle. So the other sides are going to be AB and AC. So it says, I'm just taking the figure 1 into consideration. Okay, we are not going to concentrate on the figure 2 as of now. We are going to take only the internal division in the first instance. So Triangle ABC is there. AD is the internal bisector of the angle A, and in that case we have to prove that BD by DC is equal to AB by AC. So it's given that AD bisects angle A, which is angle BAC, and we have to prove that the bisector divides the base. So it divides the base into the ratio BD by DC in the same ratio as the other two sides. So the other two sides are AB by AC. So this is what we have to prove. This result again can be used directly in the questions that you solve later on. You don't need to prove it each time, and this is a very important result. Okay, so this is in case of internal division. Let's see how we prove it. Now for proof we have to construct. In the figure it's already constructed, but the construction is draw. You have to draw CF parallel to AD. So you already have AD, you know where AD is. Okay, so C is a point that you know. From C you draw a line parallel to AD. This is going to be our construction for this question. If CF is drawn parallel to AD, what do we have? We have this BF as the transversal. Okay, so if this angle is say theta, this angle will be theta by corresponding angle. Okay, and this is theta. This has been divided internally. AD has bisected the angle D, so BAD is theta, then angle DAC is also going to be theta. Now if that is done, again AD and CF are parallel lines, AC is the transversal, so if this is theta, this angle would also be equal to theta, right? If angle DAC is theta, then angle ACF will become theta from alternate angles, right? And if angle BAD is theta, then angle AFC is going to be theta by corresponding sides. In the triangle ACF, we have AF equal to AC because the base angles are same. So the sides, opposite sides are going to be the same in the triangle, and it becomes an isosceles triangle. Okay. Now this does not help us so far, but we use the Thales theorem, and then this makes our job easier. So now AD is parallel. If AD is parallel to CF, then we have BD by CD equal to AB by AF. From which theorem? From Thales theorem. Okay. We have constructed CF parallel to AD. Hence from Thales theorem, BD by CD, which is the ratio of the sides, is equal to AB by AF. Okay, in the triangle BFC, if you look at. Okay, so this is true. Now we see that in the proof that we need, the left hand side we have got BD by DC, but in the right hand side we have AB by AF. Just now we also saw that, or we can prove here, that let angle BAD equal to theta. Okay, so let's assume it's called theta. Then angle DAC is equal to theta, as AD bisects angle BAC. It's given that AD is the bisector. Also, angle BAD or angle BAD equal to angle AFC equal to theta by corresponding angles. How is that corresponding? Because AD is parallel to CF. Okay. Also, angle DAC equal to angle ACF equal to theta by alternate angles. Okay. If these two angles are same, therefore we can say that angle AFC is equal to angle ACF. Therefore AC is equal to AF. Okay. Now if AC is equal to AF, what do we have from 1? This is 2. Using 1 and 2, what do we have? BD by CD is equal to AB. Instead of AF, I can very well write AC, because AC has come out to be equal to AF. So instead of AF in the equation 1, I can easily simply go ahead and write it as AC. And once when I write AC, this is what we had to prove, right? This is what we had to prove, that the bisector of the angle, vertical angle AD, bisects the base in the same ratio as the ratio of the other two sides. So AD bisects the base in the ratio BD by CD, and it is said that it will bisect it in the same ratio as the other two sides, and the other two sides are AB and AC. So you get BD by CD is equal to AB by AC. This is a very important result that you need to remember. So you have a triangle ABC in which the vertical angle is bisected. So AD is the internal angular bisector of angle A, then BD by DC is equal to AB by AC. So this result you have to use in questions that we'll be solving. Okay. Now this is the case of internal division, which was easier to grasp, easier to understand. The second case is when you have external division. So you have the triangle ABC. Okay, you have the triangle ABC, and angle A is externally bisected. So angle A internally will be bisected this side. Externally you have to extend BA to the other side, and then you have AC and AE, and then you do the bisection and you get AD as the bisector. Okay, you get AD as the bisector, and these two angles are going to be same. All right. Now just like in the case you have given, you can say that AD bisects angle CAE. Since it's external division for angle A, you have to write the external angle A, which is angle CAE. Now AD bisects CAE, therefore angle CAD equal to angle DAE equal to theta. Okay, this angle we assume to be theta. Now again you construct. Again, what do you have to prove? You have to prove the same thing. You have to prove that, what does AD do? AD divides the base into ratios BD by CD is equal to AB by AC. Right? D divides the base is BC in the ratio BD by CD. It's called external division in this case because the external angle is bisected. So if you have studied coordinate geometry, the point D divides the side BC, although it is lying external to it, divides it. We say that it divides the line BC externally in the ratio BD is to CD. So this is what we have to prove. And BD by CD will be equal to the other two sides of the triangle. Since base is BC, the other two sides are going to be AB and AC. So this is what we have to prove. BD by CD is equal to AB by AC. Okay. Now you construct similar as in the last case. So you construct what? CF parallel to A. Okay. You construct CF parallel to AD just like we did in the last case. If you remember, what did we do? Or we have deleted it. So CF parallel to AD is what we draw. Once we draw this, therefore we get angle ACF will also be theta by alternate angle property. Okay, by alternate angle property you get this, and also you have AC angle AFC is how much? It will also be theta because it will be equal to angle DAE by corresponding angles. Okay, so by corresponding angles, angle AFC is also going to be theta. So you have this as theta, this as theta. So you have thus AF is equal to AC. This is what you have. Now CF is parallel to AD, therefore CF is parallel to AD will imply that BC by CD is equal to BF by AF. Okay, this is what you will be getting by using Thales theorem. So you have by Thales theorem, this is going to be true. Add 1 on both sides. You add 1 on both sides. So you have 1 plus BC by CD is equal to 1 plus BF by AF, which will mean that CD plus BC by CD is equal to AF plus BF by AF, which implies CD plus BC is what? It's BD. So you have BD by CD. On the right hand side you have AF plus BF, which is AB by AF, which is 2. Okay. Now using 1 and 2, AF is again equal to AC. So using 1 and 2, we have BD by CD is equal to AB by, instead of AF, what we can write? We can write AC. And this is what we had to prove. Hence, this is, okay, so this is what we had to prove. Let's see this again, because again this is a bit complicated to understand since it involves external division. So what happens here in this case is you have angle A, internal bisection will occur inside the triangle, external would be the external angle A. External angle A is CAE. So you bisect it and let the line meet the extended base at the point D. So D externally divides the line BC in the ratio BD by CD. So it said that if the external bisector of the angle A would divide the base in the same ratio, which is BD by CD, as the other two sides. The other two sides are AB and AC. So we again have to prove that BD by CD is equal to AB by AC. Okay. So given that AD bisects angle CAE, we can say that angle CAD equal to angle DAE is equal to theta, because AD bisects the angle CAE. Now you construct CF parallel to AD just like in the case of internal division. Therefore, angle ACF that you can see here, which is right over here, where is it? You have ACF equal to CAD, which is equal to theta by alternate angle property, and angle AFC is equal to angle DAE is equal to theta by corresponding angle property. Now if angle ACF and angle AFC are equal, what do you see in the figure? If these two angles are equal, which would mean AF will be equal to AC. We call this equation 1. Now it's given that CF is parallel to AD. We have constructed CF parallel to AD, which will imply from the Thales theorem that BC by CD is equal to BF by AF. Look closely at the figure. BC by CD will be equal to BF by AF if CF is parallel to AD. You add 1 on both sides of the equation. Once you add 1 on both sides of the equation and take LCM and take the sum, you get on the numerator side of the left hand side, you get CD plus BC, and on the right hand side you get AF plus BF. Here when you take the LCM, you get CD plus BC on the numerator side, which is equal to CD plus BC is equal to BD from here. CD plus BC is equal to BD, right? So you can write BD in place of that, and on the right hand side you have AF plus BF. What is AF plus BF? AF plus BF is equal to AB. So this equation becomes BD by CD is equal to AB by AF. From 1 we have AF equal to AC, so we can get rid of the AF here and write AC instead and let the other things remain the same. So we get BD by CD is equal to AB by AC, and this is what was required to be proven. So remember again, if there is a triangle ABC in which the vertical angle is internally or externally bisected, then the bisector would intersect the base at some point within the triangle or outside. Okay, wherever it bisects, it will divide the base into two parts, BD and CD. And the ratio of these two parts, BD by CD, will be equal to AB by AC. In the questions for class 10th, you will get internal division. The external part would most probably be missing in the questions because that will make it visualization of the problem very difficult. But the internal division thing, you must use it, and there'll be some questions we'll be covering or in the assignments where this will be taken care of. So you have to remember this very important corollary. Okay, now the third corollary is essentially the converse of the corollary 2. So again, when you're taking geometry or when you're taking triangles, it becomes a bit boring and becomes very complicated, uh, learning about the constructions that you have to do and getting back to the theorem. So I'm going a bit slow here, and in case you're not able to follow it, what I would suggest is after the lecture gets over, you take some time off and view the revision video once again and try to solve the questions that are provided in the assignment. And if you're not good at geometry so far, it will take some time. So don't get unduly worried if you're not able to grasp the whole concept in case you're not very good in geometry. Geometry always takes time. Okay, the construction. Some people ask me, some students ask me, why, how did you know that we had to construct such and such? Now, this has no defined answer. It comes with practice and it comes with solving questions similar to that, in questions which are similar in nature to the question where you constructed. So it will entail a lot of practice before you can master geometry. So till the time that you're able to do that, you try to learn the concepts. You also try to figure out what the construction is. So if you get a similar question, you'll get a hang of it, and probably working around and constructing would help in that case. But if you say that upfront there is a formula by which you can actually know whether you need to construct or not, then that is not possible. Okay, so this is the corollary. This is going to be the last one for this particular lecture. Then we are going to be in a bit more exciting phase where we will just, I'll give you some time to practice some questions. Okay, so let's use our mind to one last corollary that we have now. So okay, so the corollary says that if the base of a triangle is divided internally or externally in the ratio of the sides, the straight line drawn from the point of division to the vertex bisects the vertical angle internally or externally. Now, to make things a bit simpler, we are not going to take up the external division. The external division aspect is for academic interest because it will not be asked in your exams most probably. So this question, you can take it up after the class once you have understood the previous corollary and this one as well, the internal division part of it. And just to revise and just to recheck whether your concepts are clear or not, you can attempt that. If there is a problem that you face, you can ask me or you can post the doubt and I'll respond to it. Okay, so we'll just take the internal division part of it, otherwise it's going to shoot above your head. Okay, so it's given in the triangle, it's given that BD by CD is equal to AB by AC. Where is it given? It says that if the base is divided internally in the ratio of sides, if the base is divided by the line AD, by a straight line AD, the base is divided in the ratio BD is to CD. It's divided in such a way, if the base is divided internally or externally in the ratio of the sides. And what are the sides? AB and AC. So BD by CD is given to be equal to AB by AC. Then we have to prove that AD bisects angle BAC or the angle A. So let's say let angle BAD barabar X and angle CAD barabar Y. Okay, so these two angles, we don't know what their values would be. Okay, and we construct, again we construct, draw CE parallel to AD. Just like in the last case, we draw a line CE parallel to AD, the given line AD. AD is not given to be the bisector, it's just a line that divides the base in the ratios of the sides. Okay, so we construct this and since we have drawn it parallel, so from Thales theorem we have BD by CD is equal to AB by A. Okay, and this is given, and this comes to be true from Thales theorem, okay, or the basic proportionality theorem, either one. And what do we see from 1 and 2? From 1 and 2 we see that the left hand sides are equal. So you have AB by AC equal to AB by A, equating the right hand sides because the left hand sides are equal. The numerator gets cancelled out, so you have AC equal to A. Okay, you have AC equal to AE. Again, again you have AD parallel to CE by construction. Therefore, angle BAD will be equal to angle AEC equal to X by corresponding angles. Okay, and angle DAC will be equal to angle ACE equal to Y by alternate angles. Okay, now from 3 AC is equal to AE, therefore angle AEC is equal to angle ACE. Let's call this equation 3 rather than this one. So from 3 we can say AEC is X and ACE is Y. So you have X equal to Y. So if X equal to Y, which means AD is bisecting the angle, which implies AD bisects angle A of triangle ABC. Angle A, which is angle BAC in the given figure. Okay, so just keep your mind on this for 2 more minutes and then we are going to the questions. So you have, this is given. So it's given that the base of the triangle is divided in the ratio as the sides. So we have BD by CD equal to AB by AC. Let's take angle BAD is equal to X and angle CAD equal to Y. This is assumed. Okay, so it's assumed. So we construct, just like in the last case, we draw CE parallel to AD. And since we have drawn CE parallel to AD, from Thales theorem we have BD by CD is equal to AB by A. From 1 and 2, we see that the left hand sides are same, so right hand sides can be equated. When they are equated, the AB gets cancelled out and you have AC equal to A. When AC equal to AE, which means it's a isosceles triangle, you have angle AEC is equal to angle ACE. Again, AD is parallel to CE, therefore angle X, BAD will be equal to angle AEC. So this is X, this will be X by corresponding angle. If this is Y, this is going to be Y by alternate angles. Now from 3 we have AEC equal to ACE. And what did we get? AEC as X and ACE as Y. So you have X equal to Y. When X equal to Y, which means these two, the measure of these two angles is same, thus AD bisects angle A of the triangle ABC. This is what you have to prove and this is what the corollary is. So in a triangle, the angular bisector of the vertical angle is going to divide the base in the ratio of the sides. And if a line divides the base in the ratio of the sides, then that line is going to be the angular bisector. This is what corollary 2 and 3 mean. So this is where we draw an end to the lecture, and I hope you got it. In the revision, you can definitely practice the question or listen to the video again and try to clear the concepts that you were not able to. And if the problem still persists, then maybe you can just drop me a mail or you can post it out in the doubt section and we will be taking it up later. Okay, fine.